Hello everyone. For those who joined us recently, my name is Alireza and I'm chairing this morning's session of LIDS Student Conference, which is on machine learning and statistics. Now I'm going to briefly introduce someone who really doesn't need an introduction. It's our great pleasure today to have Professor Montanari from Stanford here. Of course, many of us at LIDS are inspired by his contribution in statistics, learning theory and information theory, for which he has been recipient of several awards, including CNRS Bronze Medal for Theoretical Physics, ACM Sigmetrics Best Paper Award, and NSF Carrier Award in 2008, Okava Foundation Research Grant in 2013, and Applied Property Society Best Publication Award in 2015. He has also been an Information Theory Society Distinguished Lecturer, and in 2018 he was an invited speaker at the International Congress of Mathematicians. And today he's going to talk about his recent work on optimization in the Sherrington-Kirkpatrick Hamiltonian. Please join me in welcoming Professor Montanari.
So, thanks a lot for the invitation. I hope everybody can hear me. So I must say I'm very glad to talk here because in 2001, when I was just finished my PhD thesis, I visited LIDS for 3 months, and then that contributed a little bit of my shifting from physics to everything else. Okay, so today's talk is going to be, somehow very much related to physics, but from a different perspective and very theoretical. So if you wonder about the applications of this, ask me at the end, right? I don't think there is really any. But I think it's very interesting. Okay, so I'm looking at this problem. Okay, so this at least appeared in yesterday talk by Nina. So I'm optimizing a quadratic form over the discrete hypercube. The twist here is that I'm interested in a very specific matrix that is a Gaussian matrix, a GOE matrix that is n by n. And what does this mean? Okay, this means that this is a symmetric matrix, and the entries above the diagonal are IID, normal 0, 1 over n. This normalization is just for convenience, and the diagonal entries are IID, normal. Okay. The standard way to do it is 2 over n, but it doesn't really matter. Okay, okay, this model was introduced in 1975 by David Sherrington and Kirkpatrick, and what is the Hamiltonian here? The Hamiltonian is simply the cost function. Okay, just to stick to the tradition, I use the physicist tradition, that is to normalize this by factor 2. Okay, so this was a model for disordered magnetic materials called spin glasses, but that's not really the point here. I want to look at this as an optimization problem. Okay, so opt will be just the maximum of this Hamiltonian. Okay, and so the first question you might want to ask as a mathematician, if you're interested in this random variable, this of course is a random variable. One of the first questions that you want to ask is the limit. So we will be interested in large n, and for large n asymptotic, you're interested in wondering whether this exists. Okay, so this was proved to exist by Francesco Guerra and Fabio Toninelli in the early 2000s. I don't remember the date exactly, and the value of the limit was as, characterized rigorously in a celebrated paper by Michel Talagrand. I think 2006, And a different, a somewhat different and more powerful proof was given by Dmitry Panchenko a few years later. Okay, so I want to tell something about what is the value of this limit. The value of this limit is characterized by what is called Parisi's formula. Okay, so the reason why I want to go over this formula is twofold. First, because it plays a role in then what the question that I want to ask, and second, that it tells you something about how interesting is this problem. Right? So let me explain the formula. Okay, take a measure mu. This is a probability measure over the interval 0, 1. Right? Take your favorite probability measure, and then, I'll call mu t just the probability, the measure assigned to the interval 0, t. Okay, for t indeed. So it's the CDF of this measure. Fix a number beta non-negative. This is the inverse temperature, and then solve this partial differential equation. This is a Hamilton-Jacobi equation that I'll solve backwards in time with boundary condition at time equal 1. The boundary condition is log 2 cosh of x. Okay? So this is a parabolic PD. You solve it from t equal 1 backwards to t equal 0. Okay? And out of the solution of this equation, you construct a functional that I call P for Parisi, beta of mu. So this is a functional on the space of probability measures on 0, 1, which is just the solution. So let phi mu, I'll just write phi mu to show that this depends on mu, evaluated at time 0 at point 0, minus a linear function of mu. Okay, so what is the theorem here? So this is was a formula that first was proposed for the asymptotic value of this problem by Parisi. So this was in the late 70s, and the theorem by Talagrand it says the following. So it's not about the opt, but it's about a more complicated object that is the partition function. So instead of maximize over sigma, I take a weighted sum over sigma, a generating function, the partition function. So for large beta, this concentrates on the maximum, is dominated by maximum. You can think of it as a smooth max. And what it proves is that almost surely, if you rescale, okay, this depends on n, this is equal to the mean over this space of p beta. Okay, and if you are interested in the opt, not in this partition function, is actually simple corollary. You see, as I said, for large beta, this should be, z of beta should be about e beta, the max of this. So it makes sense that if now I take 1 over n of opt, this is equal to the beta infinity limit of this formula. Okay. So this is a simple corollary, and actually there is a direct formula at beta direct equal infinity formula that was proved by Haffinger and Chen, I think a couple of years ago. This, okay? So did what I write make sense, at least syntactically, even if not semantically? This is the kind of things that, you know, I don't know you, but when I see, I'm blown away, right? Because, you know, you start with something, this is pretty innocent, you know that if this was over the unit sphere, this would be the maximum eigenvalue, the limit of the maximum eigenvalue of a given metric is 2. Well, you know, perhaps you might get something more complicated, you know, instead of 2, 3/2 or something else, and no, something very complicated emerges, you know, Hamilton-Jacobi equation, a variational problem over the space of probability measures on the interval 0, 1. Where does this all come from? And okay, some of you are control theorists, and you know you like this type of equations because they are related to stochastic optimal control. And you might wonder, okay, is there a hidden stochastic optimal control problem into this? And in fact, there is, and you will see by the end of the, perhaps you will see a glimpse of it by the end of the talk. There was a question?
I was curious, so in this notation, replica symmetric corresponds to what?
So okay, now there is a whole, okay, this whole theory is not limited to the spatial model, but to a more generic class of models. And you know, you always obtain variational problems of this type, and depending on the you know, qualitative features of this solution mu, this optimizer mu, you distinguish different classes of model. And if mu has a point mass at a single point, you call it replica symmetric. A point mass at 2 points, you call it 1 RSB, and so on. Okay. Okay, so now, okay, so if you are into optimization, of course, you might be worried about, does this mean on the right-hand side exist? Can I compute it? After all, it's a problem in an infinite dimensional space. And of course, people asked this question, and, okay, remark. So this Haffinger, Chen, 2015, and also Jagannath, Tabasco, 2016. Okay, they have different proof the following: that the map mu to p beta of mu is strongly convex. It's easy to see that it's lower semi-continuous, but they prove that it's strongly convex. And therefore it has a unique minimizer, okay? And in fact, people solved it numerically for a while and computed the value, this value. So if you call this P star the value of the beta infinity limit, this was computed numerically by many people. The most precise calculation that I found is by Schmidt, that in his PhD thesis gives this number. Did I make a mistake? I was about to check with you. A nice upper bound is square root of 2 over pi. So this upper bound is by, again, Guerra, by Francesco Guerra.
Andrea, so what do you know about this number? I mean, is it transcendental?
No, I don't know anything.
Does it relate to any other?
In fact, one of the biggest open questions in the whole theory, and I mentioned this in a minute, is whether what is the qualitative feature of the optimizer. Physicists or simulations suggest that if you look at basically the CDF is continuous until some point, and then it has a jump. So in other words, it's a delta function plus a density. That's the expectation on the basis of simulation, but this was not proved. And actually this has important consequences, if you see in a moment. Okay, so on the basis of this, it seems to be true that the support of the optimizer, that's called mu star the optimizer, is an interval. So this is, on the basis of simulations, this appears to be true, and physicists have argument to believe that it is true. Okay. So what is the question that I want to ask here? There is a lot of interesting computational questions related to this problem that physicists didn't really, or they have ideas about, but didn't study formally. And the simplest one is the most immediate one is the following: is there a polytime? Okay, is there for any epsilon positive a polytime algorithm such that outputs sigma alg, let's call it. This is a function of my matrix A, such that sigma alg A sigma alg 1 over n is bigger or equal than 1 minus epsilon 1 over 2 opt with that probability. So what I ask, I fix an epsilon arbitrarily small. I would like to have an algorithm that outputs an 1 minus epsilon optimum in polynomial time. Okay. So this is an interesting question. Of course, the problem is hard in worst case and hard, within a constant factor. But of course, this is an average case, so that doesn't say much about it. So I'll spend a little bit of time into trying to convince you that the answer to this question is non-obvious. Okay. So why Q is, or the answer to Q is non-obvious? And this is somehow, well, my discussion will be a little bit heuristic, but you forgive me. Okay, so one piece of evidence is David, actually, this is a very recent paper, proved that computing, okay, and you'll correct me, the partition function exactly is hard under some standard complexity theory assumption. Okay, so this is about not computing the opt, but computing exactly the function. So this is, it's suggestive. Well, of course, doesn't answer this question because first of all, I'm computing a more difficult object and computing a sum, and second, I'm trying to compute it exactly. A related question here is asking whether you can compute the ground state, the optimum exactly. I believe the answer to that in polynomial time. My guess would be not, but I don't know.
Can you tell me what exactly means?
Exactly means computing something that is an exact optimizer, as opposed to a 1 minus epsilon optimizer.
Can you do arbitrary number of digits?
No, just outputting sigma such that this is equal to this.
Oh, okay.
The absolute maximum. Here I'm only asking for a maximum up to an epsilon fraction. Okay?
It's equivalent to say that you want to actually find the ground state because it's unique.
Yeah, or finding a ground state. Yeah, exactly. Yeah, it's a unique up to a flip. All right, so the natural idea that one might have is to try to study a relaxation. Okay, so the standard computer science approach to this problem would be to try to relax it. Okay, and the simplest relaxation would be a spectral relaxation, and this would be maximize half sigma, let's say 1 over 20 sigma, subject to sigma equal n. Okay, so you relax to the sphere from the hypercube. Right? This, of course, the optimizer of this is the top eigenvector of A, and we know everything about it. In particular, we know that the top eigenvalue, so this is the top eigenvalue of A divided by 2. We know that as n goes to infinity, this converges to 1. Well, so this is off by factor 75%, and if you expected that if you round it, you don't get anything particularly good. Or you don't get an arbitrarily good approximation. The next relaxation you might want to look at is an SDP relaxation, and this would be max, let's say 1 over 2n always ax subject to x. So this is the Gomans-Williamson relaxation. This actually we studied a couple of years ago with Subabrata, and one thing that we proved is that as n goes to infinity, this goes again to 1. So again, if you solve this SDP and you round it, you don't expect to get any arbitrarily good approximation. Of course, this topic is full of very interesting questions for smart people like the ones in the audience. And one natural question is here, is what about, we know that this is only one of the simplest convex relaxation you can construct for this problem. There is a whole hierarchy. So what about higher levels? In the XOS hierarchy. And I don't know the answer to this question, depending on whether the day is sunny or not. I believe that it will work on it. I really don't have any idea, but look, in fact, SOS would do something more than what I'm requiring here, because it would give you a certificate. So SOS is answering a harder question than what I'm asking here. The next thing that you might want to try are greedy algorithms. For instance, this is typically what physicists do simulations with. You start with any configuration sigma, and you start flipping one spin at a time to improve the energy, or you might do something stochastic version of that, like simulated annealing. Right? There is not a lot of analysis, rigorous analysis of that. There is a recent theorem. This is by a bunch of people. So this is Dario. So et al. Is Luc Devroy, Gabor Lugosi, and Roberto Oliveira. They proved that if you look at the expected, so this was in physics, was a result by Bray and Moore. I compute the expected number of local maximum of this function with value that is about n times v. Okay, local maxima would mean configuration whose energy cannot be increased by flipping one spin, and what they proved is that this is exponential, and this rate function I of v is something that is positive in an interval, and Parisi values here. Okay. Now, of course, this doesn't tell you that there is actually an exponential number of local maxima in the typical instance. So that is another problem, open problem. So question, open problem, prove exponential. This is what physicists believe, exponential number of local maxima with high probability. It can be that the expectation is just dominated by rare samples in which there is a huge number of local maxima, but on a typical instance it's actually easy. Physicists did a lot of calculation of this kind of quantities and believe that, non-rigorous believe that there is actually an exponential number of values of maxima, but we don't know rigorously. Okay? So numerically, if you do greedy, get stacks at energy less than P star times some constant. Okay. Okay, final piece of information. Something that is very interesting about this type of problem is trying to study the geometry of the function h of sigma. And what I mean by geometry is typically means looking at the level set. So for any epsilon, I can try to look at the set of sigma such that h of sigma is bigger or equal than 1 minus epsilon times opt. So, you want to understand, what is the structure of, this function, whether it's easy to optimize or not. You would expect that, if this convex, this level set will be nice convex set for each epsilon. You might expect to understand whether this is hard or easy to optimize it by looking at this. And okay, and this is again a physics conjecture, not yet proved. But the conjecture looks like this, that for any q in the interval 0, 1, the probability that exists sigma 1, sigma 2, such that in the level set epsilon, this is for any epsilon positive, such that the scalar product sigma 1, sigma 2 is about nq. So what I'm doing here, I'm looking at this almost optima, okay, almost optima, and I'm looking at two of them, okay? And I'm asking that I search for two of them that are not close to each other, but they are distance, a scalar product q. Now, if this function was nice and convex, you would expect that this is non-zero only if q is very close to 1, or the local optima are very close to the a single point. But instead, what I mean by this really is n of q plus small o of n. The expectation is that this is basically 1 minus small o of 1. And this actually was proved, this type of picture, by Haffinger-Chen, 2017, for a different model, okay, a spherical model. This is a different model that has some features, and I'll mention it again later, as a lot of features of this Sherrington-Kirkpatrick model, but on which a lot of calculations are much easier.
Can I ask again, can you say that what you expected was a nice set, or it was a little faster?
So if this h was a nice function, what you would expect for this probability, you would expect it to be non-zero only if q is very close to 1. Right? Because you would expect, if this is my space, my hypercube, here the global optimum, if I move epsilon above, I have a small ball, etc. Okay? So this is the picture of the level sets for a convex function, for a nice function. Instead, this is saying that the level sets for this thing, and and there are not that many local optimizer, global optimizer. So they span the space, but there is not a lot. So, particularly if you expect that level set is less than e to the minus n times some function of e to n, some function of epsilon, where s of epsilon goes to 0 with epsilon. So you expect this, for small epsilon, this thing to be something quite complicated. Okay, in fact the expectation is different, but it is small. It has small volume, but there are points at all possible distances. There are pairs of points at all possible distances. Okay. Again, this is not proved, but gives an idea of why this should be not easy to optimize.
If that conjecture is true, does that imply that the support of new star is needed?
Yeah, I don't know if it implies directly, but it's of course it's related, right? Does it imply directly? Probably yes, for beta large numbers. I mean, you have to see, because it depends, this is telling, it's not exactly the same because it's telling there is two configurations. It might be that the configurations are completely isolated, so there is an entropic factor by which in the Gibbs measure they disappear. So it's not completely obvious, but it's more or less the same. Okay, so I hope by now perhaps I convinced you that the question is a little bit interesting. So what is the answer? Okay, so what is the answer? So there is an assumption here that I stated at some point. I mean, this is about the solution of this problem. And the assumption is that as physicists believe, for any beta large enough, the support of mu star, the optimizer, this is called the Parisi measure, is actually the interval, an interval. Well, this is a value depending on beta. Okay? So it's actually saying that the measure behaves as I showed, the CDF behaves as I drew it here. Okay? This is again what you see numerically, what people expect physically, and it's an interesting open problem if you want in analysis. Okay? So under this assumption, the theorem is the following. For any epsilon positive, there exists an algorithm with complexity at most C of epsilon times n square that outputs such that with high probability, what I claimed before holds. Okay, so at least I've been thinking about this for a while actually, and try to convince people that this was true, but people would push back about this. Finally, I'm happy that this is true. Okay, so I should add a remark here. Perhaps. So there is a paper, and this was also a big inspiration, by Eliran Subag last year, also a few months ago. It solves in the same direction a similar problem. And okay, let me describe what is the similar problem solved by Eliran. And the similar problem is optimizing a random tensor, random polynomial really, over the unit sphere. Okay, so what does it mean, a random polynomial? It means simply that I take a tensor of order 3 and I multiply by sigma I, sigma j, sigma k, plus, it's important for this result that the polynomial is not homogeneous, so there will be a C3 and then perhaps a C4 I, j, k, L, sigma I, sigma j, sigma k, sigma L, and here the convention is that indices repeated are summed over, etc., and all of these are Gaussian random variable, independent Gaussian random variable. So this is a random polynomial over the sphere. For some choices of this coefficient, this picture that I described here is true. This is the picture that Haffinger-Chen proved. So the level sets somehow form this web that span the whole space in a way. And for this type of polynomials exactly, Eliran proved that you can optimize this thing in polytime. So I should say two things about this solution. One is that it's beautiful. It's really beautiful. In the sense it's one of these things that you see it, and it's a one-page proof, 2 pages perhaps. And it's really very nice, once you understand the way to do it, and he understood it. The other thing is that it's probably quite difficult to extend to the +-1 case, because it uses quite heavily the geometry of the sphere, okay? It uses quite heavily the geometry of the sphere that we don't have here. Okay, so I think that this program can be possibly pushed to this, I think, case, but it's...
What's the maximum degree? I mean, it's a little bit weird that it's not homogeneous. Like, is there, suppose that I want to stop at degree 5, can I do it, or?
Yeah, you can do it, So there are conditions on the now it takes me a little bit of time there is a simple condition on the coefficient that is a completely explicit that you can check. If that condition holds, then this picture is true. You can write the Parisi formula, and it's like this. And exactly the condition holds. Haffinger-Chen proved that the level sets have this property. So in the case of the spherical model, these 3 pieces of the puzzle, the solution to the variational problem, the algorithm, and the picture of the landscape have all been settled. In the Ising case, they have not been settled, but under the assumption, this theorem proves that the assumption gives an algorithm. Okay, so now I should say perhaps. So any question about this, perhaps?
There's no normalization here?
Yeah, there is here. Let's see. Yeah. So these have to be all so normal of variance of order 1 over n. Okay, and so you take all of these. So these are over order 1, and then there are some constant factor that to vice versa.
Sorry, and the condition on the C sub j is some kind of correlation condition?
Yeah, it's okay. So it's something of this type. So the C are deterministic. They just give the variance of the different set, and the condition is the. Now I'll write it wrong because I don't remember the normalization correctly. But it's something of this type. You look at the generating polynomials of this. So this is a generating polynomial. You look at the second derivative of this, and then you ask that either the square root of the second derivative is concave or the inverse of the square root of the second derivative is concave. I don't remember which one, but it's a completely explicit condition, if you give me. And there are simple examples with a mixture of 3 guys that satisfy this condition. So in that case, the calculations are quite easy. Now, what happens in that case basically is that the variational problem that I described before over the space of measures. So there is this variational problem that I described with the PD and blah, blah, blah. In that case, the PD, there is no PD, and the variational problem is explicit in U and can be solved exactly. So you have an explicit formula for everything, somehow. Here we don't have an explicit formula for the optimizer. Any other question? So perhaps I spend a few minutes discussing the proof and the analysis. But again, this optimizing polynomial on the unit sphere I didn't mention, but obviously is also an NPR problem in worst case. All right, so the algorithm is a message passing algorithm, okay, it's an approximate message passing. So this is a kind of algorithm that I've been thinking about for a while, and for which we developed over the years some technology, and also ties back in some way to LIDS, because it's related, of course, to Bob Gallagher. But okay, here it's in a very transformed way. So you start with a vector, so you construct a sequence of estimates. The initialization is a Gaussian, standard Gaussian vectors, and then you update this vector by something of this form. you have a power term, gk xk minus 1. So all of these are vectors. Let me write them like this to emphasize this. uk, and then to subtract a term, gk minus 1, xk 2 minus 1, k minus 1. Okay, so you start with a vector, and then you update this vector how. This is a function that acts on this vector xk, xk minus 1 that I'll define in a moment. This is Hadamard product, entry-wise product, and then multiplied by this method. Okay? And then I subtract some term. Okay? So here gk are some function, scalar function, and I apply them component-wise. So gd for a vector v is gd1, gdn. Okay? And what is this vector xk? Okay, so I stopped writing the underline. So if you forget this, basically the x's are the running sum of the u's. Now they are not the running sum of the u's, they are modifying them by some extra kind of drift term. And the end of the day, I accumulate this increment. So this is z is equal to square root of delta and then gk xk minus 1 okay. So here the idea somehow is that and this will be my estimate for the truncate. So sigma that I output is just rounding of z. Right, so again, I start with a random vector, and then I construct this sequence of random vectors. If this g were 1, I would be doing power iteration, and I will be computing the top eigenvector of the matrix in some form. Instead, this term is present. This is crucial to obtain an object in the interval 0, 1. I mean, you want in the end the z to be close to a plus minus 1 solution, so that is crucial. And the factor by which it's scaled depend on all the history of the use. Okay. So one nice fact. So why this thing is that this whole class of algorithms, and in fact more than this, there is a way to analyze them. There is a whole technologies to analyze them. GK is any function. It's any sequence of functions. So this is it's a whole class of functions, and so it has to be Lipschitz continuous. But apart from that, well, I'll fix it at the end. But
can I take 0?
Yeah, you can take it. So this will give you a sequence of a class of algorithms, a very broad class of algorithms, because it depends on these G's and then these B's and etc. So in general, this algorithm will give you garbage. Will give you garbage unless you come up with the right sequence of function G and the right sequence of functions B. If you come up with the right sequence of function G's and the right, I claim that this thing will output a near-ground state. Now the question is how on earth I come with the right sequence of function G's and B's. A priori I don't know, but the nice fact about this type of algorithm is that under some regularity condition on G of B, I can get the exact analysis in the n to infinity limit. So I can characterize So I can characterize, so for any sequence of functions gk and b, I can characterize the limit as the number of dimension goes to infinity. So I fix the number of iteration fixed, I keep the number of iteration of this algorithm fixed, and I'll take n to infinity, and what happens is that I can exactly understand the distribution of this, very precisely understand the distribution of these objects, and compute the value that we achieve. And this, of course, will depend on the sequence of function gk on the function v, and then I'll try to engineer the function v and g to make things work nicely.
We also need to fix the bk's and the...
Yeah, so this is completely, so these are some coefficients that are completely determined by the rest. Okay, so this is a scalar, and is determined by the gk's. So it's not...
I see, it's not independent.
So it's you fix it in a certain way to make things work. So somehow the scalar here is, this subtraction here is what makes things independent. Okay, so this kind of analysis, I can't go in detail over it, but this was developed over several years, and the rigorous part started with Erwin Bolthausen, and then we extended in all possible way with Mosse and Bayati, Adelja Van Maart, and others. So this is 2011. Now, the key remark here is that something very interesting happens, is that if you choose, construct the algorithm this way, the u's become asymptotically orthogonal. So UK, UL, and if you normalize things correctly, if G are chosen, G is normalized, this converges to a delta function. So if you think now of how I'm constructing, so think of this as the solid hypercube. I want to construct in the end a point that is one of the vertices of the hypercube. And the way I'm constructing is that I'm summing a bunch of increments. Forget this. If these weren't there, I would be summing a bunch of orthogonal increments. So I'm doing, okay, this is not really correct. Okay. I'm doing some kind of random walk that starts from the origin and get there, right? And this makes a lot of sense. So my intuition, I didn't analyze precisely, but my intuition is depending on the initialization, we land on different corners of the hypercube, and this somehow matches this intuition about the structure of optima, right? Since you have many optimizers that can be also orthogonal between each other, you want an algorithm that doesn't always converge to the same point. You want an algorithm that somehow follows a random path, but a random path that depends on the distribution of your specific instance. Now, in reality, these are not all the increments are not orthogonal because this is in there, and you would expect that this is important because otherwise you wouldn't end up on the corner, right? You wouldn't end on the surface of the sphere. You want to end up in the corner. So it's important that I scale this. In particular, this factor such that if the current average is close to 1, you don't increment it anymore. Okay, if you design the G's correctly. Okay. So the nature of the algorithm is this type. You follow a path. Perhaps it's worth saying in the p-spin model, in Eliran's problem, the spherical problem, these increments are orthogonal, and this is what makes somehow that analysis much. I think it's easier. In this case, the increments are not orthogonal. So how the analysis goes now? So I said that the analysis can be done as n goes to infinity. So I take n to infinity first, and then I add this small step size square root of delta. So I take delta to 0. So think of delta as a very tiny constant, okay? And n infinity. So in that limit, the behavior, what happens is the behavior of this x, U converge to a sequence of IID Gaussian, so the sums of U converge to a Brownian motion, and X, so distribution of X is captured by the following stochastic differential equation. dxt equal bxt t dt plus beta dbt. You see, I have a sequence of orthogonal, think of this now as random variables. I have a sequence of orthogonal random variables, and I'm adding them up. So it makes sense that this sequence will converge to Brownian motion. And so this is the Brownian motion. So in fact, the sum of the U, the running sum of the U, converge to a Brownian motion. And if that's true, then the sequence of the X should converge to a diffusion driven by that Brownian motion. So indeed, it converges to this. So the precise statement is, if you want the, for instance, if you look at any Lipschitz function, and you look at some test function over x chi I, this converges to when n goes to infinity, delta goes to 0, with k times delta equal t, this converges to the expectation of psi xt. So xt really is telling me what is the distribution of the coordinates of this thing. In other words, you can think of these vectors as really as random variable in a certain probability space in the larger limit. Okay? So this is the process that drives the algorithm. And what is the value? Again, if you take delta to 0 and to infinity, and then you look at the value that you achieve, sigma alg A sigma alg. This is given, well, you do a calculation and you get, this will be related to that function g, and in fact is given by the integral of the expectation of g xt t dt. So this is the value that you obtain. So any sequence of function, so here I'm taking gk x to be g of x and k delta. Right? So any two function g and d will give me an algorithm, and this algorithm will achieve exactly this value, where x is determined by that stochastic process. Okay? And so at this point you can try to design what is the optimal algorithm in this class. Okay? I have to design the function g and the function v, and what I want to satisfy, I want to maximize the integral between 0 and 1 of the expectation of gxt t dt. This is the value of the problem, subject to, there is the condition that I mentioned, but I a little bit swept under the target, is that the u's are always normalized, and this boils down to the condition on g, and this is that e of g x t. Okay, so this is the normalization, this is the value. Now, if I had only these two things, you would have an easy solution. What is the solution to this? What is the value of this problem? I claim that the value of this problem is 1, right? Just by Cauchy-Schwarz. by Cauchy-Schwarz, this is less than 1, and this exactly 1 by replacing G equal 1. Okay? And this is not surprising because the thing I encoded here, I didn't code the fact that the coordinate must be between -1 and 1. So what I'm getting is the optimum of this quadratic function over the sphere. So here in the description of the algorithm, I didn't write anywhere that I wanted the end z to be in the interval -1, 1, or to be close to ±1. In fact, this gives you an algorithm, a very complicated algorithm, or a very complicated way to compute the maximum eigenvalue of a random matrix. Now, how do I enforce the condition that has to be equal to ±1? Yeah. Well, you saw what is z. So in the limit, z is described by a random variable z, that is the integral between 0 and t. So there will be g xt t, and then will be u that it goes to the Brownian motion. Okay, so the value of the coordinate is encoded by this, and what you want them to be in the interval -1, 1. So in the integral 0, 1 of g xt t, dbt must be -1, 1, almost sure. Right, so now I don't know anything about contrast here, right? But many people here know a lot, and in fact I didn't solve the contrast theory problem. I knew Paris's formula, and I guessed from Paris's formula what is the form of G and D. But you can solve this as a stochastic optimal control problem. After that I studied optimal control. It's a nice problem. You have a particle moves under the diffusion. You have to design the control in such a way that in the end this integral hits this interval at the end of the time, and somehow this power is 1. And the solution is exactly this time. Okay, so if you solve this, you can add a duality constraint for this, and the dual constraint that corresponds to this is exactly the measure mu, Paris's measure mu. Okay? Yeah, so this, you do this, and then you get exactly this value, so this achieves the optimum.
So did you use the assumption on the support that you mentioned in the beginning?
Where did I use the assumption of the support? It's a good point. I use it in a bunch of places. Okay, this whole analysis is general. Then when you plug in things, this whole analysis is general, and this problem is general. In fact, as I said, it's not even related necessarily to ±1 variable, right? But then when I plug specific values and compute the value of this specific values of G and D, and have to check that this match somehow the dual value that is given by Parisi formula, then I have to use the full support assumption. Okay, that's all. Thank you.
Questions?
So does this solution already suggest that if you wanted to optimize the quadratic form with respect to some other kinds of constraints, so maybe not over the hypercube but over some other set, would you expect a similar solution to work in general? Or?
Yeah, I mean, so as I said now, so the constraint must be the way I can impose the constraint. If I want to get this simple description, the way I can impose the constraint easily is on the empirical distribution. Okay, so if you tell me, okay, I want to maximize sigma a sigma subject to the empirical distribution of sigma, so new sigma. Here we impose that the empirical distribution is delta at +1 plus delta at -1. I can impose that this is some other things, or belongs to some set, right? Or this is equal to some specific, or it's approximately equal to some specific value. For instance, you want to maximize over all vectors that are 30% plus 1, 30% minus 1, and 40% zeros, right? So you will get the same problem. All the analysis is the same, except that now you will get this with this, the empirical distribution of this random variable. The distribution of this random variable must match mu bar, and you will get a formula here. And okay, so you can do kind of generalized SK model. Now, if you want to put some kind of non-separable constraint, probably if the constraint is simple enough, you can do it. So we have an analysis of this kind of algorithm that generalized to function. Here I took this function g and b that are separable, but we have an analysis that generalized to function g's and b's that are not separable. So perhaps if you want to maximize these over some other sets that is not separable, you might be able to do it. But okay, I don't know exactly what you get at the end of the day. So it might be interesting to try.
Do you believe that Markov chain will be natural Markov chain if the constructor will be mixing fast?
Right. No, mixing fast. No, I don't believe that. But so the natural Markov chain Glauber dynamics. If you do simulations, people did a lot of simulations. You don't get fast mixing above beta equal 1. But on the other hand, something interesting happens that if you do simulated annealing, then you converge to the optimum energy. You converge very slowly, but you seem to converge. This is okay. There are unpublished simulations that enough, but you converge very slowly. So I would think that simulated annealing does it, achieves optimal, but my guess is that it does it with a worst constant C of epsilon. So this will be still C of epsilon n squared. So it will be simulated annealing on physical times of order 1. But it will be, okay, if you look at the plots, they go very slowly to the ground state energy.
Do you have theoretical reasons?
No, I don't have theoretical reason. I mean, there is some work that is non-rigorous analyzing Glauber dynamics by Cugliandolo and Kurchan. They wrote some kind of partial differential equations for the evolution of simulated annealing, and then they solved them heuristically. That suggests that it does it, but I think it's very difficult. I mean, I think it's very interesting. Actually, I spent some time trying to follow that route. I think it's very interesting. I think also it's very difficult. Here, I mean, okay, the proof is relatively simple. If you say it's not that, it uses some technology, but it's not good.
What part uses that it's SK rather than some other?
Well, you could do other models. I think, for instance, I think I can do without difficulty Opfield model. Or I can, these separable constraints also can be treated. Of course, this will give you an algorithm for any of these problems. Now, this will be I think it will match the optimum only if, the measure is fully supported otherwise.
So what does this G look like?
Question. So,
or somehow when you implement this, you get some approximation.
Okay, so G really, okay, it's a good point. So this G turns out to be either the first or the second derivative of the solution of the Paris PD times some beta square factor. I think the Paris. So this function looks like. Goes on one hand, I think it's the first or the second, I don't remember. So the first derivative looks like the hyperbolic tangent, so it goes to plus, but it's not exact, it goes to +1. And so here, okay, I should have stated things precisely. The theorem assumes that you have access to a solution of this. That I think it's a reasonable assumption given that people solved it.
So it's a reasonably small function.
Yeah. You can think that it's nice and stuff like that.
So, I'm not sure what the correct notion of planting is, but you could imagine that there would be a kind of planted version of the problem where maybe you rotate the matrix of one of the eigenvalues close to its sign vector or something?
Well, the simplest planted version of the problem is that you do the spiked model, right? So x0 transpose plus w, right? So this is a GOE matrix, and this is plus minus 1 vector, this is, and then we try to figure out x0.
Right, so do you think that this type of technique will work also to get
yeah, so I think if you do this, you will get, so the picture here is that this, I mean, it will not beat the hardness for this inference problem. It will not beat that. But the picture here is that you can try to do with, do the base optimum, and there is a message passing algorithm for this that starts estimating at lambda equal 1, but you can try to do the maximum likelihood estimator. So this will give you an algorithm that computes the maximum likelihood estimator for this problem, I think, for this problem, but for any lambda bigger than 1. Okay? So the maximum, the point is that, okay, this is interesting. It's not hard shortening because we already have an algorithm that computes the base optimal estimator for this problem. Now, another interpretation of your question is, can I use planting as in pseudo calibration to prove hardness?
No.
Okay.
I mean, there's other notions of planting that might be the appropriate ones for pseudo calibration that aren't like planting and spike. And I just wonder if for those plantings this would work as an algorithm. Because I guess my understanding is very limited, but you drew this picture of this hypercube and the random walk, and it seems like if you're going to end up at any good point, there's no reason that you would go to the planted one.
Right, exactly.
So
how do you want to plant things here?
You could imagine rotating the matrix a little bit so there's an eigenvector that has value not 1, but like a little bit better than 0.76, whatever. It's a sign vector, right?
Right, yeah.
And there maybe you could get that one.
No, I don't
No, okay.
get this one. Right, I mean, because the picture is always there.
Okay.
So if there is not any other question, let's thanks Professor Montanari again. So this wrap up our morning